On the 15th of January 1947, a classified memorandum circulated through the corridors of the Air Ministry on King Charles Street. Operational requirement 330, stamped with the highest security classification available to the peacetime RAF, outlined specifications that seemed to belong more to science fiction than to the drawing boards of British aviation. The air staff demanded a bomber capable of carrying a 10,000-pound atomic weapon to targets 1,500 nautical miles distant, at speeds approaching 500 knots and at altitudes exceeding 50,000 feet. The men drafting these requirements understood a brutal truth. The Soviet Union would soon possess atomic weapons of its own, and Britain's survival depended upon aircraft that could strike Moscow before Soviet defences could react. The strategic logic was grimly straightforward. Intelligence assessments from the Joint Intelligence Committee, based at the Cabinet Office on Whitehall, indicated that Soviet radar networks and interceptor forces were expanding rapidly. The piston-engined Lincoln bombers, then equipping Bomber Command, would be obsolete within 5 years. Any replacement aircraft would need to fly so high and so fast that ground-based anti-aircraft artillery would be rendered useless, and contemporary fighters would lack the ceiling to intercept. Altitude in this calculus was survival. 3 British aircraft manufacturers received invitations to submit designs: Avro, Vickers, and Handley Page. Each company approached the problem differently. Avro, under chief designer Roy Chadwick, proposed the delta-winged Type 698 that would become the Vulcan. Vickers offered the more conservative swept-wing Type 660, destined to enter service as the Valiant. But at Handley Page's facility in Cricklewood, North London, the design team led by Reginald Stafford took an approach that aeronautical orthodoxy considered borderline impossible. Sir Frederick Handley Page had built his reputation on bombers. His firm had produced the O-400 of the Great War and the Halifax that had pounded German cities throughout the 1940s. Now 72 years old, Sir Frederick remained actively involved in the company's technical direction, and he insisted that the new bomber must not merely meet the air staff requirement, but exceed it dramatically. The initial Handley Page submission, designated HP-80, proposed an aircraft capable of reaching 60,000 feet, 10,000 feet higher than the official specification demanded. This was audacious. No operational military aircraft had ever sustained flight at such altitudes. The American Boeing B-47 Stratojet, then entering service with Strategic Air Command, could barely manage 40,000 feet. The prototype de Havilland Comet airliner, the most advanced British jet transport, was designed for a ceiling of 42,000 feet. To promise 60,000 feet required either exceptional confidence or exceptional engineering. Handley Page possessed both. The key figure in transforming this ambition into technical reality was Godfrey Lee, the company's chief aerodynamicist. Lee had spent the war years analyzing captured German research on swept wings and high-speed flight, and he understood that the fundamental barrier to extreme altitude was not engine power, but wing design. At heights above 50,000 feet, the air density drops so dramatically that conventional wings generate insufficient lift without flying at speeds that approach the transonic region. But transonic flight in 1947 meant encountering shockwaves that could tear an aircraft apart or render its controls ineffective. German research from the Aerodynamische Versuchsanstalt at Göttingen had demonstrated that sweeping a wing backward delayed the onset of these compressibility effects. Yet swept wings brought their own problems. They tended to stall unpredictably at their tips first, causing catastrophic loss of control. The Air Ministry's own research establishments at Farnborough and Bedford were wrestling with these contradictions, and no consensus existed on the optimal solution. Lee's answer was the crescent wing, a planform that had never been attempted on any production aircraft. Rather than applying a uniform sweep angle across the entire span, Lee proposed varying the sweep progressively, from root to tip. The inner sections, where the wing was thickest and generated the most lift, would be swept at a sharp angle to delay compressibility. The outer sections, where thickness diminished, could afford a gentler sweep, maintaining controllable stall characteristics. The result resembled a graceful curve rather than the angular geometry of American or Soviet designs. It was, on paper, elegant. Whether it would work in reality remained to be proven. The mathematics behind the crescent wing emerged from Godfrey Lee's office at Cricklewood across 18 months of intensive calculation, wind tunnel testing, and theoretical refinement. Lee's central insight was deceptively simple. The critical Mach number at which compressibility effects begin to degrade lift is not constant across a wing, but varies with local thickness to chord ratio. A thick wing root encounters transonic buffet at lower speeds than a thin wing tip. By adjusting the sweep angle to compensate for these variations, Lee could engineer an aircraft where the entire wingspan reached its critical Mach number simultaneously, rather than suffering the piecemeal breakdown that plagued conventional designs. The practical geometry that emerged specified a sweep angle of 45 degrees at the wing root, reducing progressively to 35 degrees across the intermediate section, and finally 20 degrees at the outer panels. Each section blended smoothly into the next, creating the distinctive, curved leading edge that would make the Victor instantly recognizable. Wind tunnel models tested at the Royal Aircraft Establishment Farnborough throughout 1948 confirmed Lee's predictions. The crescent planform delayed drag rise by approximately 0.05 Mach, compared to a conventional swept wing of equivalent area. A seemingly small figure that translated into thousands of additional feet of sustainable altitude, but altitude capability demanded more than aerodynamic refinement. The Victor's wing also needed to be structurally efficient enough to carry fuel for the specified range, whilst remaining light enough to climb into the stratosphere. Here, Handley Page's structural engineers faced a problem that no British manufacturer had previously confronted. At 60,000 feet, the pressure differential between the pressurized crew compartment and the near vacuum outside would exceed 8 pounds per square inch. The fuselage would need to function as a pressure vessel whilst simultaneously bearing the aerodynamic loads of high subsonic flight and the concentrated stresses of carrying a 5-ton nuclear weapon in its bomb bay. The solution adopted a semi-monocoque construction using newly developed aluminium-zinc alloys that offered superior strength-to-weight ratios compared to wartime materials. Specification DT D5700 alloy, produced to Air Ministry standards at facilities in Birmingham, formed the primary structure. The pressurized section was limited to the forward fuselage, accommodating a crew of 5, 2 pilots seated side by side beneath a fighter-style canopy, and 3 rear crew members, the navigator, radar operator, and air electronics officer, housed in a windowless compartment that bomber crews would come to call the coal hole. This crew arrangement departed significantly from the wartime Lancaster and Halifax, where gunners occupied positions throughout the aircraft. The Victor carried no defensive armament whatsoever. Speed and altitude were its only protection, a philosophy that reflected the brutal mathematics of nuclear warfare. If Soviet fighters could reach 60,000 feet, defensive guns would merely add weight that reduced ceiling and range. If they could not reach the Victor, guns were unnecessary mass. The air staff accepted this logic without sentiment. By late 1948, the HP-80 design had matured sufficiently for the Ministry of Supply to issue specification B35/46, formalizing the requirement around Handley Page's proposed capabilities. 2 prototype aircraft were ordered under Contract 6/Aircraft/8535, with construction authorized at the company's facility at Park Street in Hertfordshire, away from the cramped Cricklewood site. The first prototype, serial WB.771, was allocated to aerodynamic testing. The second, WB.775, would evaluate systems integration. Construction proceeded through 1949 and 1950 against the backdrop of rapidly deteriorating international relations. The Soviet Union had detonated its first atomic bomb in August 1949, years ahead of Western intelligence predictions. The Berlin blockade had demonstrated Soviet willingness to challenge Western positions by force. In Korea, Communist forces would soon pour across the 38th parallel. Each development reinforced the urgency of Britain's nuclear deterrent program, yet the Victor remained, stubbornly, a collection of components rather than a flying aircraft. The crescent wing structure proved exceptionally difficult to manufacture. The compound curves required forming techniques that pushed British industry to its limits, and the tight tolerances demanded for aerodynamic efficiency meant rejection rates for major components ran distressingly high. At Handley Page's Park Street facility, skilled craftsmen discovered that the theoretical elegance of Lee's design translated into practical nightmares when aluminium sheets refused to assume their mathematically specified profiles. The first prototype would not fly until Christmas Eve 1952, nearly 6 years after the original specification had been issued, and fully 3 years after the simpler Vickers Valiant had taken to the air. Squadron leader Hedley Hazelden lifted WB-771 from the runway at Boscombe Down in Wiltshire at 14 minutes past 10 on the morning of the 24th of December 1952. The weather was cold but clear, ideal conditions for a first flight that the entire British aviation industry had awaited with considerable anxiety. Hazelden, a vastly experienced test pilot who had previously evaluated the Valiant prototype, kept the undercarriage extended throughout the 30-minute sortie as a precaution against hydraulic failure. His initial report to Handley Page was cautiously optimistic. The Victor handled remarkably well for so unconventional a design, though longitudinal stability required further investigation. The test program that followed would consume 3 years and claim 1 aircraft. WB-771 completed 263 flights before being retired, systematically exploring the Victor's performance envelope whilst engineers at Cricklewood refined production drawings based on accumulated data. The second prototype, WB-775, joined the program in September 1954, equipped with more representative systems, including the complex bombing and navigation equipment that operational aircraft would carry. Power plant selection had proven contentious. The original specification assumed engines delivering approximately 10,000 pounds of thrust each, figures that seemed optimistic in 1947 but proved conservative as turbojet technology advanced. The first prototypes flew with Armstrong Siddeley Sapphire SAE.7 engines, each producing 11,000 pounds of thrust, respectable but insufficient for the performance margins that operational doctrine demanded. The Sapphire was a reliable engine derived from the Metrovic F2 program that had originated during the war, but its specific fuel consumption at altitude was mediocre and its development potential limited. Rolls-Royce offered an alternative. The Conway, designated RCO-11 in its initial military configuration, represented a fundamental departure in jet engine philosophy. Rather than passing all ingested air through the combustion chambers, the Conway ducted a portion around the core as bypass flow, improving propulsive efficiency dramatically. This bypass principle, pioneered by Rolls-Royce at their Derby facility, would eventually dominate civil and military aviation. In 1954, it offered the Victor something more immediate: 20,000 pounds of thrust with fuel consumption nearly 15% lower than equivalent pure turbojets. The Air Ministry authorized development of the Victor B Mark II specifically around the Conway. Production Mark I aircraft would enter service with the Sapphire, providing initial operational capability, whilst the more capable variant completed development. This parallel approach reflected both urgency and pragmatism. Bomber Command needed aircraft immediately, but those aircraft needed room for improvement as Soviet defences evolved. The Sapphire-powered Victor B Mark I achieved its service ceiling of approximately 55,000 feet through careful management of aircraft weight and atmospheric conditions. Crews learned that altitude capability varied significantly with fuel load, external temperature, and the precise condition of their individual aircraft's engines. A lightly loaded Victor in cold winter air could reach 57,000 feet. The same aircraft on a humid summer day, carrying full fuel and a Blue Danube weapon, might struggle above 52,000. The Conway transformed these margins. Test flights of the B Mark II prototype, serialed XH668, demonstrated sustained flight above 60,000 feet, the figure that Godfrey Lee had promised a decade earlier and that many in the Air Ministry had privately considered fantasy. At this altitude, the curvature of the Earth became visible to crews, the sky above deepening from blue to near black. External temperatures dropped to minus 56 degrees Celsius. Pressurization systems labored to maintain a cabin altitude equivalent to 8,000 feet, and any failure would incapacitate the crew within seconds. The achievement was not merely theoretical. Operational squadrons would routinely fly at these heights, their aircraft leaving condensation trails so thin and high that ground observers could barely perceive them. This was the altitude sanctuary that British strategic doctrine demanded, a realm where Soviet interceptors could not follow, and surface-to-air missiles of the 1950s lacked the kinematic energy to reach. The physics were unforgiving. At 60,000 feet, air density is approximately 7% of sea level values. An aircraft maintaining 500 knots indicated airspeed is actually travelling through the air at over Mach 0.9 relative to the ground, approaching the transonic regime where Lee's crescent wing earned its keep. Engine thrust diminishes proportionally with air density, meaning power plants must work far harder to generate equivalent forward momentum. The margins between controlled flight and aerodynamic catastrophe narrowed to knife-edge tolerances. The Victor operated in this environment not through brute force, but through elegant engineering. The comparison that gives this account its title requires precise examination rather than casual assertion. The English Electric Lightning, which entered RAF service with No. 74 Squadron at Coltishall in June 1960, represented the absolute pinnacle of British interceptor design. Its two Rolls-Royce Avon turbojet engines, mounted in an unprecedented stacked configuration, delivered a combined thrust exceeding 30,000 pounds with reheat engaged. The Lightning could climb from brake release to 40,000 feet in under 3 minutes, a performance that no contemporary fighter anywhere in the world could match. Yet this extraordinary machine, designed specifically to reach and destroy high-altitude bombers, could not reliably intercept a Victor flying at its operational ceiling. The fundamental explanation lies in the distinction between absolute ceiling and combat ceiling. Any aircraft can, under ideal conditions, struggle momentarily to its maximum theoretical altitude. Sustaining controlled flight at that altitude, maneuvering, tracking a target, firing weapons, is an entirely different proposition. The Lightning's absolute ceiling approached 60,000 feet in clean configuration with minimum fuel. Its combat ceiling, the altitude at which it could meaningfully engage an adversary, was closer to 54,000 feet. Above this height, the aircraft's maneuverability degraded so severely that any evasive action by a target would leave the interceptor wallowing, unable to complete a firing solution. Flight Lieutenant Roland Beaumont, chief test pilot at English Electric and the man who had conducted the Lightning's maiden flight from Warton in Lancashire, understood these limitations intimately. In his technical reports to the Ministry of Supply, Beaumont documented the phenomenon known as coffin corner, the narrowing envelope at extreme altitude where stall speed and maximum speed converge toward a single value. At 55,000 feet, the Lightning's margin between stalling and encountering compressibility buffet shrank to approximately 40 knots. Any aggressive maneuver risked either condition, both potentially fatal. The Victor faced identical physics, but from a fundamentally different operational requirement. A bomber need not maneuver aggressively. Its mission demanded straight, level flight at maximum sustainable altitude, maintaining a precise heading toward its target whilst the navigation and bombing system computed weapon release parameters. The crescent wing, optimized for sustained high-altitude cruise rather than combat agility, excelled in precisely this flight regime. Where the Lightning fought to reach 60,000 feet and could barely function there, the Victor cruised at that altitude with margins to spare. Official RAF documentation from the Air Historical Branch records operational profiles during exercise Double Quick in September 1961 that illuminate this disparity. Victor aircraft from No. 10 Squadron, based at RAF Cottesmore in Rutland, penetrated simulated Soviet airspace at heights between 58 and 61,000 feet. Lightning interceptors from No. 56 Squadron at Wattisham attempted intercepts under ground-controlled interception direction from radar stations at Bawdsey and Neatishead. Of 14 attempted engagements, only 2 achieved simulated weapon release parameters, both against Victors that had descended below 56,000 feet due to technical malfunctions. The Victor crews were acutely aware of their advantage. Squadron leader John Harrington, a pilot with No. 15 Squadron at Cottesmore, later recalled the psychological comfort of operating above the interceptor ceiling. Radar warning receivers might illuminate with tracking signals from ground stations, but crews knew that the fighters scrambling in response would exhaust themselves climbing before reaching engagement altitude. The bomber's defense was passive, but absolute, simply remaining where the enemy could not follow. This advantage extended beyond British airspace. Intelligence assessments of Soviet protivo-vozdushная Obrona fighter capabilities suggested that the MiG-19, then the backbone of Soviet air defense, could barely exceed 55,000 feet under any conditions. The more advanced MiG-21, entering service in numbers from 1959, improved this ceiling to approximately 59,000 feet, still marginally below the Victor B Mark II's operational altitude. Soviet pilots, like their RAF counterparts, would find that absolute ceiling figures bore little resemblance to combat capability. The geometry of interception compounded these difficulties. A fighter approaching a bomber from below must climb whilst closing, bleeding energy against gravity. The bomber, already established at altitude, sacrifices nothing. By the time an interceptor clawed its way to the bomber's height, fuel reserves would be critically depleted, and missile launch parameters potentially unachievable. The Victor's 60,000 feet represented not merely an altitude, but a tactical sanctuary, temporary certainly, but sufficient for the strategic calculus of the 1950s and early 1960s. The strategic purpose underlying all this engineering elegance resided in unremarkable buildings scattered across the flat agricultural landscapes of Lincolnshire, Yorkshire, and East Anglia. By 1961, the Victor equipped 4 operational squadrons within No. 3 Group Bomber Command, numbers 10, 15, 55, and 57, with the first 2 based at RAF Cottesmore and the latter pair at RAF Honington in Suffolk. These units formed part of the V-Force, Britain's airborne nuclear deterrent, operating under conditions of readiness that placed immense strain on both aircraft and crews. Quick reaction. Alert demanded that a proportion of the force remain at immediate readiness throughout every hour of every day. At each V-Force station, aircraft sat in dispersed locations around the airfield perimeter, armed with live nuclear weapons, their crews either in the cockpit or within seconds of reaching it. The state known as Alert Condition 2 required crews to be airborne within 15 minutes of warning. Alert Condition 1 reduced this to 4 minutes. In the event of confirmed Soviet missile launch, those 4 minutes might represent the entirety of Britain's response window. The weapon that gave the Victor its strategic significance was the Blue Steel standoff missile, a complex and temperamental system that multiplied both the bomber's reach and the readiness complications. Blue Steel was powered by an Armstrong Siddeley Stentor rocket engine, burning kerosene and hydrogen peroxide, propelling a warhead of approximately 1 megaton yield to targets 100 nautical miles distant from the launch point. This standoff capability meant that Victors need not overfly heavily defended targets directly. They could release their weapons from the relative safety of altitude and distance, complicating Soviet defensive calculations considerably. The missile resided semi-recessed in the Victor's bomb bay, its distinctive shape visible from below as a bulged protrusion that disrupted the aircraft's clean lines. Maintaining Blue Steel at operational readiness required continuous monitoring of the hydrogen peroxide oxidizer, a substance sufficiently volatile that ground crews treated it with profound respect. Specialist vehicles attended each armed aircraft, their operators trained to detect the slightest indication of propellant instability. The Air Ministry's original vision of nuclear deterrence through simplicity had evolved into something far more complex. Air Marshal Sir Kenneth Cross, who assumed command of Bomber Command in August 1959, articulated the doctrinal framework within which these aircraft operated. The V-Force existed, Cross argued in submissions to the Chiefs of Staff Committee, not to fight a war, but to prevent one. Soviet strategic planners, contemplating aggression against Western Europe, would confront the certainty that British bombers would penetrate their defences and devastate their cities. The Victor's extraordinary ceiling was not a technical curiosity but a strategic necessity, the foundation upon which credible deterrence rested. The targets assigned to each squadron were designated by the Joint Inter-Service Group for the study of all-out warfare, operating from the Joint Planning Staff offices at Storey's Gate near St. James's Park. These target folios, classified at the highest level, allocated specific Soviet cities, military installations, and industrial complexes to individual aircraft and crews. A Victor pilot at Cottesmore might spend his entire operational tour training to destroy a target he knew only by coordinates, never by name, aware that the mission would likely be one way. Flight profiles for nuclear strike missions assumed that no recovery to British bases would be possible. Even if the aircraft survived Soviet defences, the United Kingdom they had departed would likely be devastated by retaliatory strikes. Crews trained for diversions to neutral nations, to emergency landings in Turkey or Iran, to any fate preferable to turning back toward radioactive ruin. These considerations hung unspoken over every readiness period, every practice scramble, every hour spent confined to the alert caravan, waiting for klaxons that mercifully never sounded. The routine was simultaneously tedious and terrifying. Crews rotated through quick reaction alert periods typically lasting 24 hours, confined to purpose-built facilities near their dispersed aircraft. They played cards, read novels, slept fitfully, always within reach of the telephone that connected directly to the bomber controller at High Wycombe. Practice alerts occurred without warning, crews scrambling to their aircraft and running through start sequences, whilst officers with stopwatches recorded their performance. Any crew failing to meet the required response times faced immediate remedial training. The pressure proved considerable. By 1963, RAF medical officers were documenting elevated rates of stress-related illness among V-Force aircrew. The altitude sanctuary upon which British nuclear strategy depended began eroding before the Victor B Mark II even entered operational service. On the 1st of May 1960, an American Lockheed U-2 reconnaissance aircraft, piloted by Francis Gary Powers, was destroyed over Soviet territory near Sverdlovsk. The weapon that brought Powers down was the S-75 Divina, known to NATO as the SA-2 Guideline, a surface-to-air missile system that fundamentally altered the calculus of high-altitude penetration. Intelligence assessments reaching the Joint Intelligence Committee throughout 1960 and 1961 documented the rapid proliferation of SA-2 batteries across the Soviet Union. The missile itself was substantial, 35 feet in length, propelled by a solid fuel booster and liquid fuel sustainer, capable of engaging targets at altitudes exceeding 70,000 feet. This ceiling surpassed anything that British bombers could achieve, regardless of engineering refinement. The physics that had protected the Victor, the simple inability of threats to reach its operating altitude, no longer applied. The guidance system presented additional concerns. The SA-2 employed command guidance with ground-based radar tracking both the missile and target, computing intercept solutions and transmitting steering corrections via radio link. This methodology had limitations. It could be jammed, confused by electronic countermeasures, or overwhelmed by multiple simultaneous targets, but against a single bomber flying a predictable straight-line penetration profile, the system proved devastatingly effective. Powers had been flying at approximately 70,000 feet when the missile detonated nearby, shredding his aircraft with fragmentation damage. Air Marshal Cross and his staff at High Wycombe confronted an uncomfortable reality. The V-Force's entire operational concept assumed that altitude conferred immunity. Blue Steel's 100-mile standoff range offered partial mitigation. Bombers could launch from beyond the engagement envelope of point defense missiles protecting specific targets. But the SA-2 was being deployed not merely around Moscow and Leningrad, but in an integrated air defense belt across the Soviet Union's western approaches. Penetrating to launch points would require traversing hundreds of miles of defended airspace. The response developed across several parallel tracks. Electronic countermeasures equipment, previously considered secondary to performance characteristics, became urgent priorities. The Victor B Mark II received the Red Steer tail warning radar, capable of detecting approaching missiles and fighters, coupled with jamming systems operating across the frequency bands used by Soviet tracking radars. Window, Strips of metallic chaff could be dispensed to create false radar returns. These measures offered degradation of enemy capabilities rather than immunity, buying time and complicating firing solutions without guaranteeing survival. More fundamentally, tactical doctrine shifted from high-altitude penetration toward low-level attack profiles. At heights below 1,000 feet, ground clutter rendered radar tracking extremely difficult, and the SA-2's guidance system lost effectiveness entirely. The terrain-following approach that Bomber Command had previously dismissed as unnecessary now became essential training. Victors designed for the stratosphere would need to thunder across Soviet territory at treetop height, relying on speed and concealment rather than the altitude sanctuary for which their crescent wings had been optimized. This transition proved operationally demanding. The Victor's airframe, stressed for the relatively benign loads of high-altitude cruise, accumulated fatigue damage far more rapidly when subjected to the turbulence and maneuvering of low-level flight. The elegant crescent wing flexed visibly during aggressive terrain following, its structure-absorbing punishment never anticipated by Godfrey Lee's original calculations. Crew workload increased substantially, navigation becoming exponentially more challenging at heights, where radar horizons shrank to mere miles. Simultaneously, Soviet interceptor capabilities continued advancing. The Sukhoi Su-9, entering service from 1959, carried air-to-air missiles rather than relying solely on cannon armament. The MiG-21, in its later variants, could engage targets at altitudes approaching 60,000 feet with the K-13 missile, a Soviet copy of the American Sidewinder, heat-seeking and difficult to evade. The assumption that fighters could not reach the Victor's altitude grew increasingly questionable. By 1964, classified assessments circulating within the Ministry of Defense acknowledged that the V-Force's ability to penetrate Soviet defenses was deteriorating rapidly. The transition of Britain's nuclear deterrent to the Royal Navy's Polaris submarines, announced by Prime Minister Harold Macmillan following the Nassau Agreement of December 1962, reflected this strategic reality. The Victor's days as a nuclear strike platform were numbered. The decision to withdraw Victors from the nuclear strike role did not render the aircraft obsolete. Instead, the airframes entered a second career that would ultimately prove more consequential than their original mission. Conversion to the tanker configuration began in 1965, with the first K-Mark I aircraft entering service with No. 55 Squadron at RAF Marham in Norfolk during 1966. The Victor's capacious fuselage, originally designed to accommodate nuclear weapons, adapted readily to carrying fuel for transfer to other aircraft. The conversion program exploited the Victor's fundamental strengths, whilst abandoning capabilities no longer relevant to its new role. Internal fuel tankage was augmented substantially, total capacity reaching approximately 120,000 pounds, sufficient to extend the range of multiple receiver aircraft across strategic distances. 3 hose drum units were installed, one beneath each wing and one in the former bomb bay, allowing simultaneous refueling of 3 aircraft. The pressurized crew compartment remained functional, enabling extended missions at altitudes where fuel transfer efficiency was maximized. Flight Refueling Limited, based at Tarrant Rushton in Dorset, conducted the conversion work under contract to the Ministry of Defence. The company had pioneered air-to-air refueling techniques during the 1940s, developing the probe and drogue system that became standard across British and many Allied air forces. Their engineers understood the demanding tolerances required. Fuel transfer at 500 knots, in turbulent air, with receiver aircraft flying within feet of the tanker's trailing hoses. The Victor's inherent stability at altitude made it exceptionally suitable for this mission. The strategic rationale for maintaining a tanker force extended beyond supporting the remaining V-bombers. RAF strike aircraft assigned to NATO, particularly the Blackburn Buccaneer and later the Panavia Tornado, depended upon aerial refueling to reach targets deep within Warsaw Pact territory. Transport aircraft conducting long-range deployments required tanker support. The rapid reinforcement of NATO's northern and southern flanks, a cornerstone of alliance defensive planning, assumed available tanker assets. The Victor K Mark I and the improved K Mark II, converted from B Mark II airframes with their superior performance, became essential enablers of British air power projection. This theoretical capability was tested under actual operational conditions in April 1982, following Argentina's invasion of the Falkland Islands. The response mounted by the British government required air operations across distances that seemed almost inconceivable. Ascension Island, the nearest available staging base, lay nearly 4,000 miles from the Falklands. Striking Argentine positions on the islands demanded round trips exceeding 8,000 miles, far beyond the unrefueled range of any aircraft in the RAF inventory. Operation Blackbuck, conceived by Air Vice Marshal Michael Knight and planned in extraordinary haste at RAF Waddington and High Wycombe, proposed using Vulcan bombers to attack Port Stanley airfield. The Vulcan carried conventional bombs rather than nuclear weapons, but the tactical objective, denying Argentina use of the airfield for fast jet operations, supported the Naval Task Force's approach. The operation's feasibility depended entirely upon Victor tankers. The refueling plan that emerged was staggeringly complex. Each Blackbuck mission required 11 Victor tankers supporting a single Vulcan, transferring fuel in a carefully choreographed sequence that saw tankers refueling other tankers before themselves returning to Ascension. The mathematics were unforgiving. Any mechanical failure, any missed rendezvous, any miscalculation of fuel consumption would leave aircraft stranded over empty ocean. Wing Commander David Maurice Jones, commanding No. 55 Squadron's contribution to the operation, later described the planning as the most demanding of his career. Blackbuck 1 launched in the early hours of the 1st of May, 1982. 14 aircraft departed Wide Awake Airfield on Ascension, 11 Victors and 2 Vulcans, 1 primary and 1 reserve. Fuel transfers began almost immediately, aircraft maneuvering into formation behind trailing drogues in darkness over the South Atlantic. 1 Victor suffered a refueling probe failure and turned back. A Vulcan's cabin pressurization malfunctioned, forcing the reserve aircraft to assume the primary role. Despite these complications, the mission proceeded. The Vulcan reached Port Stanley Airfield and delivered 21,000-pound bombs across the runway at approximately 4:15 local time. 1 bomb struck the runway surface directly, others cratered the surrounding area. The Vulcan then turned north for the equally demanding return flight, meeting Victor tankers at pre-arranged coordinates for fuel essential to reaching Ascension. The Blackbuck raids demonstrated capabilities that many had doubted existed within the post-imperial Royal Air Force. 7 missions were ultimately flown, though 2 aborted due to equipment failures, delivering both conventional bombs and Shrike anti-radiation missiles against Argentine radar installations. The strategic effect remained debated. The single runway crater was repaired within 24 hours, and Argentine fast jets never operated from Port Stanley regardless. But the demonstration of reach carried political weight beyond tactical results. Britain had projected air power across 8,000 miles of ocean, striking a defended target and recovering the attacking aircraft safely. The Victor tanker force made this possible. The aircraft that had once carried weapons capable of destroying cities now sustained operations to recover distant islands. This transformation reflected broader shifts in British defence posture across the Cold War decades. The independent nuclear deterrent passed to the Royal Navy's Resolution-class submarines in 1969, their Polaris missiles invulnerable beneath the ocean in ways that aircraft could never match. Bomber Command itself was abolished in 1968, its squadrons absorbed into the new Strike Command structure. The Victor's original mission evaporated, yet the airframe remained valuable. Throughout the 1980s, Victor K Mark II tankers continued supporting RAF operations worldwide. They refueled Tornadoes deploying to exercises in the United States, Phantoms patrolling the Falklands exclusion zone, Hercules transports conducting long-range supply missions. No. 55 Squadron at Marham maintained continuous readiness, their aircraft aging but still capable of performance that few contemporary types could match. The crescent wing that Godfrey Lee had designed for 60,000 feet cruise proved equally effective at the medium altitudes where tanker operations typically occurred. The end approached gradually rather than suddenly. Structural fatigue, the accumulated consequence of 4 decades of flight operations, imposed increasingly restrictive limitations on the remaining airframes. The low-level training that Victor bombers had undertaken during the 1960s and 70s had stressed wings never designed for such punishment. Cracks propagated through primary structures, demanding extensive inspection regimes and occasional groundings whilst repairs were effected. Each aircraft carried its individual history of stress cycles, and engineers tracked these accumulations with growing concern. The replacement arrived in the form of the Lockheed TriStar and Vickers Vive C-10, converted airliners offering greater fuel capacity and modern systems, whilst lacking the Victor's stratospheric performance. These aircraft equipped the newly formed No. 216 Squadron from 1984, gradually assuming responsibilities that Victors had held for 2 decades. The transition acknowledged industrial reality. Maintaining bespoke military tankers had become economically unsustainable when retired airliners offered equivalent capability at lower cost. The final Victor Squadron, No. 55, disbanded at RAF Marham on the 15th of October 1993. The ceremony attracted former aircrew spanning the aircraft's entire operational history, from officers who had flown the first B Mark I deliveries in 1958 to crews who had supported Black Buck missions over the Falklands. Air Vice Marshal Ron Dick, himself a former Victor captain, presided over the formal lowering of the squadron standard. 6 aircraft conducted a final formation flypast, their crescent wings silhouetted against Norfolk skies for the last time. 1 aircraft, XH-648, was preserved in taxiable condition at Elvington in Yorkshire, where volunteers maintained it in running order for ground demonstrations at airshows. The distinctive sound of its Conway engines, a deep, resonant thunder quite different from modern high-bypass turbofans, drew crowds who remembered when such aircraft had defended Britain against threats that now belonged to history. Other survivors took their places in museums at Cosford, Duxford and Hendon, their Cold War context requiring increasing explanation to generations born after the Berlin Wall fell. The Victor's legacy resists simple summary. It was a bomber that never dropped weapons in anger, a nuclear delivery system that never delivered its nuclear payload, a tanker that proved its worth in a conflict nobody had anticipated. The 60,000 feet ceiling that justified its complex design became strategically irrelevant within years of its achievement, superseded by missiles that flew higher still. Yet the aircraft served for 35 years, adapting to roles its designers never envisioned, demonstrating the value of fundamental engineering excellence over mission-specific optimization. Godfrey Lee's Crescent Wing carried British aircrew through the most dangerous decades of the 20th century. That none of them flew towards Soviet targets in earnest remains the Victor's greatest contribution to history.